Hey everybody, I'm here with my daughter right now, and we are going to give you some background information on distributed loading, referencing the Hibbler Statics textbook. So before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. And let's go ahead and get started. You ready?
In this section, we are going to be exploring what's called reduction of a simple distributed loading. And this is going to be section 4.9 in your textbook. So up to this point, if you noticed in our course, all we have discussed so far is concentrated point loads acting on our system. So now we're going to start exploring what are called distributed loadings, okay? So we're going to make a note here. We're going to say up to now, we have only dealt with concentrated, quote, point loads. Now we will explore distributed loads. Okay, so what do we mean by distributed loads? Well, what we mean is instead of having a concentrated point load, which is represented by one single vector, one single arrow, now what we're going to have is a load that is spread out over a distance, okay? That's how we're going to start anyway. Then we're going to lightly talk about loads spread out over an area. So let's make a note here. We're going to talk about loads spread over a length, and these will have units. We're going to say with units of force over length. And then we're also going to briefly talk about loads spread over an area with units of force over area. Okay, and not only are we going to explore the idea of a distributed load, but we're going to look at the location of an equivalent point load that incorporates this distributed load. So let's go ahead and get started with this background. So let's first talk about loading over a length, okay? Loading over a length. And we're going to say, consider the beam below. So let's say that we have a beam here. This is called a simply supported beam. We're going to kind of talk about what that means to be a simply supported beam later. And we're going to call W the distributed load, and we're going to call the horizontal axis of the beam X, okay? And then we're going to say that we have some load, W, spread out over the length of this beam. And again, the length of the beam, obviously, we're going to call it, well, hopefully it's obvious, we're going to call it L. And then we're going to give the name of this distributed load, W, as a function of X. So again, we have W as a function of X is the distributed load as a function of location X along the beam's length. And this far left point is our origin. And again, this little vertical axis I drew here represents like the W axis, which corresponds with distributed load. And then the horizontal axis is the X axis. Okay, so so then the question becomes, what is the total load on the beam? Okay, so here we have this load. W that's got units of force over length. Okay, so I'll even make a note here. I can say W is a function of X, has units of force over length. And make sure you make a note, this is not W times X, it's W as a function of X. This is function notation. All right, so if you have this distributed load that has units of force spread out over this length, how do we get what the total load is on the beam? So let's write this down together. Let's say that the total load, which is a force, on the beam is equal to the sum of all of the forces on the beam. Okay, so since a distributed load can be thought of as an infinite number of parallel forces, what do you think we do? We integrate W as a function of X. Okay, so then we can say the total equivalent force is ... F equals the integral from 0 to the total length of the beam of W as a function of X dx. And again, this is not W times X, it's W as a function of X. All right, so let's look at this for a second. If let's say we knew this function, W is a function of X, if we took the integral of this function from 0 to the total length that it's acting over, what we're going to get is a single force with just units of like pounds or kips or newtons, okay? Now, what have we essentially done here? Well, what we've done is found the area under the load distribution, all right? So we can make a note of this. The total equivalent force is simply the area beneath the load distribution. Okay? And that's it. Now, the simplest case of this is what we call a uniform distributed load. All right? So we're going to make a note of this. The simplest case of this is what we call a uniform distributed load. Okay, so that means that your distributed load does not vary over the length. It's a constant uniform load. Okay, so let's kind of stop this video here, and in the next couple of videos, we're going to see some examples of this. Okay.